Hey guys, we're going to be doing number 5 from the Garrett and Grisham on page 479. Sorry, let me get this corrected. Basically what it's asking you to do is take this equation and they give you a P50. They give you the partial pressure of oxygen inside the lungs. They give you the partial pressure of oxygen inside of your capillaries, which is it's right here, sorry. 40 torr. And they want to know what the efficiency is when N equals 2.8, which is the cooperativity factor. And so, means how much oxygen is your hemoglobin transporting from your lungs to your capillaries. And then I want you to do the same exact thing for when N equals 1 and comment on it. So even though they give us an equation that you may have never seen before, there's a couple ways you can go about this. You can go ahead and deviate an equation that was given to you in class by Dr. Gassier. This is the equation that they give us. You can go ahead and try and multiply this side and divide by that side and do all this fancy stuff. And you should eventually get an equation that Dr. Gassier gave you guys, which is y equals PO2 over PO2 plus P50, and these are all to the end. This is your ratio of saturation. So they give us our PO2 in lungs equals 100. They give us P50, which is going to equal 26. N equals 2.8. And the PO2 in the capillaries is going to equal 40. And then we're going to use the same exact numbers, except this time N equals 1. So how they set this up is that they basically, from here we can just plug and chug. So this is going to equal Y of the lungs equals 100, because that's our PO2 in our lungs. 100 plus 26, and this is all to the 2.8. Once you calculate this all out, you should get something around 0.977, or I like to write, just round up and say 98%. Or you can also say 0.98. Either way, it's good. So now we're going to do the same thing for Y lungs. Now we're going to do the same thing for the Y in the capillaries, which is going to equal 40. 40 plus 26, and this is all to the 2.8, 2.8, 2.8. And when you multiply this all out, Y cap is going to equal 77. So 98 minus, this is all percentages by the way, so your actual answer should be 0.77 and 0.98. So 98% minus 77 equals 21% saturation that the hemoglobin is losing. So basically for part 2, you're going to do the same exact thing, except now n is going to equal 1. So what that means is that n is, or your hemoglobin is acting just like myoglobin without any cooperativity. So each subunit of hemoglobin is like is acting like myoglobin. It's acting on its own, and it's not influenced by any other subunits of hemoglobin. So you set this up the same way. Your n equals 2, or 1, sorry. And now your y in the lungs is going to equal 79. And your y in your capillaries is going to equal 61 after you do all this stuff. All the calculations. So your efficiency is going to be 79 minus 61, which is going to equal 18%, which is your differences. This is when it's working when n equals 2.8, and this is when n equals 1. And so what's significant about this problem? One is the fact that you have to either know that this is your equation, that you can also manipulate this to this equation, and also you have to know that, or what you can do is you could just plug your numbers into here and then solve for y as well. So there's actually 3 ways that I see about doing this, but those are just 2 of them. And then so your efficiency is going to be 21% versus 18%. And so even though that isn't very different, it doesn't look very different on paper, in reality it is. A 3% of oxygen you're losing, so you have to breathe a lot more. Not only that, but if you ever exercise, you're starting off at 77% saturation. So the most you can give away is 77%. If your hemoglobin loses every little last bit of oxygen when you're running, when it's needed, or whatever. This is storing 98%. It's only going down to 77%. I'm sorry, this starts off at 79, but this goes down to 77% when it's working cooperatively. So that means if needed, it can drop another, 16% or so before it even reaches to where this hemoglobin isn't working cooperatively. So the whole point of this is showing why hemoglobin needs, to be a good transport of oxygen, needs to work cooperatively, and why this has evolved versus just having myoglobin, which is a great storage unit instead. Okay, I hope this cleared things up, and good luck.